Welcome and thank you for joining me today as we discuss resistor trade-offs and resistance drift. My name is Nathan Bailey Lundell, Director of Engineering at Venkel. Today we'll explore critical aspects of resistor performance, including material differences, stability over time, to help better understand resistance drift more effectively. Whether you're a design engineer or someone interested in optimizing circuit performance, this session is tailored for you. Let's get started. Here's what we'll cover today: a comparison between thick film and thin film resistors, understanding resistance tolerance changes in drift, key factors impacting resistance stability, and tools and models for predicting resistance drift. Our hope is by the end of this session, you'll have a clearer understanding and better insight and knowledge of how to select and optimize resistance for your applications. Resistors can be broadly classified as thin film or thick film, and the key differences lies in their material systems, manufacturing, and performance. Thin film resistors utilize materials like nickel chromium or tantalum nitride, which are deposited through a process called sputtering onto a smooth, dense aluminum oxide substrate. This results in a highly precise and stable resistor ideal for applications where accuracy is critical, such as medical devices or high-frequency circuits. In contrast, thick film resistors utilize ruthenium oxide mixed into a paste, which is then screen printed onto a less refined substrate and thermally processed. While they are less precise, the process is simpler and more cost-effective, making thick film resistors suitable for large-scale applications like household or consumer electronics. To ensure both types meet their specifications, a laser trimming process is used to fine-tune the resistance values. The choice between thick and thin film resistors ultimately depends on balancing performance requirements with cost considerations, allowing engineers to select the best option for their specific application. The way resistors conduct electricity depends on the material system and structure. Nickel chromium thin films rely on metallic conduction, where electrons move within a partially filled conduction band. As temperature increases, these electrons collide more frequently, raising resistance, a behavior known as a positive TCR. In contrast, tantalum nitride thin films show a more nuanced response based on nitrogen content. At low nitrogen levels, they behave similarly to nickel chromium, but at higher nitrogen content causes them to exhibit semiconducting properties. This leads to a negative TCR, where resistivity decreases as temperature drops, allowing for better conductivity. Lastly, ruthenium oxide thick films operate through a more complex mechanism, with electrons tunneling through particles embedded into a glass matrix. The behavior of thick films can vary significantly depending on factors like particle size, concentration, and matrix composition, resulting in either a positive or negative TCR. By understanding these mechanisms, engineers can select materials that best align with their thermal and performance requirements of their applications. Thin film resistors stand out for their precision and stability, which makes them a preferred choice for demanding applications. Their ability to maintain tight tolerances as low as 0.01% and achieve exceptionally low temperature coefficients of resistance, or TCR, ensures accurate performance even under changing environmental conditions. Thin films also offer minimal parasitic capacitance and low noise, making them ideal for high-frequency circuits and precision measurement systems. These benefits result in reliable, consistent performance over extended periods, particularly in sensitive electronic applications such as instrumentation and communication systems. Within thin film technology, tantalum nitride provides additional advantages, especially in challenging environments. Tantalum nitride resistors are highly resistant to moisture and environmental stresses due to their dense glass-like composite structure. This makes them particularly well suited for humid or corrosive conditions where other materials might degrade. In long-term testing, tantalum nitride resistors show minimum drift, particularly less than 0.05% after 1,000 hours of temperature and humidity exposure, highlighting their longevity and stability. These characteristics make tantalum nitride an excellent choice for applications where environmental protection and long-term reliability are critical. Thin film resistors, and particularly tantalum nitride variants, deliver superior precision, low noise, and exceptional environmental durability. This makes them indispensable for applications where accuracy, stability, and reliability cannot be compromised. Resistor stability is influenced by external conditions such as temperature, voltage, humidity, and mechanical or thermal stress. Over time, these factors can cause resistance to drift, impacting performance. This slide compares how thin film and thick film resistors respond to stability tests under varying conditions. Thin film resistors, including nickel chromium and tantalum nitride, demonstrate superior stability with resistance changes as low as 0.05 to 0.1%, depending on the stress applied. For example, in endurance and thermal tests, nickel chromium thin film show minimum variation, just 0.05% in most cases, even under demanding conditions like high power or rapid temperature shifts. Tantalum nitride thin films, while slightly higher, remain well within acceptable limits, making them highly reliable. In contrast, thick film resistors exhibit far greater variation, reaching up to 1% in short period overload or damp heat tests. This difference highlights the limitations of thick film technology when precision and long-term stability are required. For applications with strict performance standards, thin films offer a significant advantage, and their resistance variation being roughly 1/16 that of thick films after extended use. Thin film resistors provide far greater stability under stress compared to thick films, making them the preferred choice for high reliability applications where minimal resistance drift is critical. Resistance, instability, and drift refer to changes in a resistor's performance over time due to environmental factors such as temperature, applied voltage, humidity, or mechanical stress. These changes can manifest as an increase or decrease in resistance, typically quantified as the absolute value of drift. While traditional approaches use the arithmetic sum of variations to estimate drift, this method often overestimates worst-case scenarios, leading to overly conservative assessments. A more accurate approach is the square root of the sum of squares, or SQRTSS method, which calculates the total resistance drift by combining individual variation components in a statistically meaningful way. This model offers a more realistic worst-case prediction, ensuring that the tolerance, thermal stress, and other factors contributing to resistance changes are properly accounted for without unnecessary overestimation. Key contributors to resistance variation include factors such as short-term voltage surges, temperature fluctuations, mechanical stresses, and prolonged environmental exposure like damp heat. By understanding these components and adopting the SQRTSS model, engineers can design more reliable systems while avoiding excessive margins that inflate cost or complexity. Employing advanced drift modeling techniques like SQRTSS helps ensure precise resistance predictions, balancing performance reliability with realistic expectations. This approach enables better planning and efficiency in high-precision applications. Resistance drift refers to the long-term changes in a resistor's value due to environmental and operational factors, with temperature and power load playing dominant roles. Over time, these factors cause permanent changes in resistance, especially under sustained high temperatures. For thin film resistors, this drift is captured by a key parameter known as the absolute drift in application, or delta R of A over R of A, which represents the fractional drift in resistance relative to its initial value. The equation provided models this drift by incorporating several variables, including temperature, stress, time, and power dissipation. The critical factor here is the doubling temperature factor, T of dF, which relates the exponential nature of drift. Resistance drift doubles with every 30 degrees C increase in hotspot temperature. Similarly, the cube root of the application time, T of A, compared to a reference time, T of O, highlights the relationship between time and the rate of drift. By combining these influences with absolute drift and baseline drift, this model provides a reliable estimate of how thin film resistors behave under extended use. This model emphasizes the importance of managing temperature and power to minimize resistance drift. Proper thermal design and power derating can significantly enhance the stability and longevity of thin film resistors in high-performance applications. Over time, resistance drift in thick film resistors, particularly those using ruthenium oxide material systems, is influenced by both environmental factors and chemical reactions. One key contributor is humidity, which promotes chemical hydration of the ruthenium oxide element, forming water molecules that alter the resistive structure. This process can accelerate resistance drift, especially under high humidity conditions. The chart here compares resistance drift over time between thick film and thin film resistors under standard and high power conditions. Thick film resistors exhibit significantly higher drift, with resistance increasing by up to 20 times over 20 years under damp heat conditions. By contrast, thin film resistors are much more stable with minimal drift even under extended operating times. High-power thin film versions show slightly more drift but remain far superior to their thick film counterparts. While thick film resistors offer cost advantages, their susceptibility to environmental drift makes them less suitable for precision applications. Thin film resistors, with their superior stability, are a better choice for designs requiring long-term reliability with minimal performance degradation. Resistor drift over time is influenced by not only the temperature and power, but also by several additional factors that arise during manufacturing, assembly, and operational use. For example, hot spots near the middle of the resistor or near the tip of the laser cut are created by applied voltage and can accelerate drift. However, careful design of uniform resistor patterns and in-terminal helps mitigate this. Physical damage during the chip manufacturing board, assembly, or testing can also lead to increased drift, as can episodic stresses like voltage surges or electrostatic discharge events. Thermal shocks, such as an excessive solder reflow ramp rates or cooling rates beyond 6 degrees per second, exacerbate mechanical and thermal stresses, further contributing to long-term resistance changes. The graph here illustrates how power and temperature stress influence drift. Higher applied power and temperature lead to more pronounced drift, emphasizing the importance of carefully managing these variables in resistor applications. Designing for long-term stability requires not only selecting materials with low intrinsic drift, but also minimizing external stresses to optimize assembly, handling, and operational conditions. Managing thermal and electrical stresses is essential to ensure reliability in demanding applications. The voltage coefficient of resistance, or VCR, describes how applied voltage influences a resistor's resistance, expressed as the change in resistance per unit of voltage. This relationship is represented by the formula shown, where VCR is typically measured in parts per million per volt. Higher applied voltage can cause joule heating, which increases resistor element's temperature. This effect can amplify resistance drift, especially in material systems with higher resistivity, such as ruthenium oxide, or in smaller resistor sizes where heat dissipation is less efficient. A key aspect of VCR is its overlap with temperature coefficient of resistance effects, as heating from applied voltage can create localized hotspots within the resistor. These hotspots increase the likelihood of resistance drift over time and are incorporated into predictive drift models to ensure accuracy in high-stress applications. While the magnitude of VCR effects is often small, they can become more pronounced in specific material systems and under extreme operating conditions. Engineers need to account for VCR effects in designs where high voltage or power dissipation are expected. Proper material selection and thermal management can mitigate the impact of these effects, improving long-term resistor stability and performance. The voltage coefficient of resistance VCR is influenced by several material and design factors that determine how a resistor responds to applied voltage. The primary contributors include the material composition of a resistor element and its resistivity, as well as the length and path length of resistive element, which can affect how voltage is distributed across the component. Additionally, termination materials and the resistor's thickness can play significant roles in defining its VCR. Factors like temperature changes, hot spots, trimming geometry further influence the behavior of the VCR under real-world operating conditions. Secondary effects include phenomena such as electron tunneling, interparticle contacts, and microscopic gaps between conductive particles, which are particularly relevant in granular or composite materials. These interactions impact how efficiently electrons move through the material, contributing to variations in VCR. In practice, increasing the resistance length can reduce the voltage per unit length, thereby minimizing its VCR effect and improving stability. Understanding these factors influence VCR enables engineers to optimize resistor design for specific applications. By tailoring material choices, dimensions, and processing techniques, it is possible to reduce VCR effects and enhance overall performance in voltage-sensitive environments. Resistance tolerance refers to the allowable deviation of a resistor's actual resistance from its nominal or stated resistance value. This deviation is defined by the equation shown, where the tolerance percentage determines the range of acceptable resistance values. Importantly, this form of resistance variation is time-independent, meaning it manifests during manufacturing and does not change significantly over the resistor's lifespan. The graph here highlights how thin film resistors achieve a much tighter resistance distribution compared to thick film resistors. This tighter tolerance is due to the superior material properties and precision manufacturing processes of thin films. In some cases, the variation in thin films may be an order of magnitude smaller than that of thick films, making them ideal for applications requiring high accuracy and stability. The tolerance value represents an inherent property of the resistor and underscores the advantage of thin film technology for precision circuits. Selecting components with tighter tolerances reduces variability, ensuring consistent performance in demanding applications. Temperature coefficient of resistance, TCR, quantifies how resistor and resistance changes as a function of temperature. It is expressed in parts per million per degree Celsius and is calculated using the provided relation. TCR represents an initial time-independent property of the resistor and is influenced by the material's conduction mechanisms. Positive or negative TCR values indicate whether a resistance increases or decreases with temperature changes. The second equation shows how to determine the percentage change in the resistance based on TCR, initial resistance, and the temperature change, delta T. For example, a higher TCR value combined with large temperature shift can result in a significant resistance variation affecting the resistor stability. This behavior is particularly critical in precision applications where maintaining consistent resistance values is essential. Understanding TCR is vital when designing circuits exposed to varying temperatures. By selecting resistors with an appropriate TCR value, engineers can mitigate temperature-induced drift and ensure reliable performance across operating conditions. This graph illustrates how the temperature coefficient of resistance affects the percentage change in resistance for thin and thick film resistors over a range of temperatures. Thin film resistors demonstrate a much lower TCR, typically between 5 and 100 ppm per degree C, which keeps their resistance change minimal and well within the allowable tolerance of plus or minus 1%. This stability makes them ideal for precision applications where tight resistance control is critical. In contrast, thick film resistors with TCR values ranging from 50 to 200 ppm per degree C, typical, exhibit much greater resistance drift as temperature rises. At elevated temperatures, such as 125 degrees C, thick film resistors can quickly exceed their tolerance limits, consuming their resistance budget and compromising circuit performance. This behavior highlights the trade-offs between cost and stability, with thin films offering superior temperature resilience compared to thick films. For applications requiring precise and stable resistance across a wide temperature range, thin film resistors are the optimal choice. Their lower TCR ensures minimum drift, maintaining performance within allowable tolerance level even under challenging thermal conditions. Hotspots on resistors, often caused by localized temperature increases, can lead to increased TCR movement and greater resistance variation. Adjusting the trimming geometry of a resistor is an effective way to minimize these effects and improve voltage sensitivity. Three common trimming geometries are illustrated here. A narrow trim results in a higher voltage sensitivity because the current density is concentrated in a smaller area, increasing the likelihood of hotspots. By contrast, a wide trim distributes the current more evenly, reducing sensitivity. The top hat trim further optimizes current distribution, minimizing voltage sensitivity and ensuring the most uniform resistance behavior. For thin films, trimming can lead to a positive VCR as electron movement increases resistance to conduction band behavior. In thick films, trimming may result in a negative VCR influenced by avalanche effects within the material. This highlights the importance of tailoring trimming techniques based on the resistor type and application requirements. Proper trimming geometry significantly impacts a resistor's performance, reducing hotspots and optimizing voltage sensitivity. Choosing the right geometry ensures greater stability and reliability in high-precision circuits. This table provides a comparative overview of the strengths and weaknesses of resistors made from ruthenium oxide, nickel chromium, and tantalum nitride. Each material has its unique attributes that make it suitable for specific applications. Nickel chromium thin film resistors offer a balance between cost, precision, and performance. They provide tight tolerances with values as low as 0.01% and low TCR and VCR ratings, making them well suited for high frequency and low noise applications, such as RF circuits or instrumentation. However, their humidity resistance is relatively low, which can limit their use in harsh environmental conditions. Tantalum nitride thin film resistors excel in its stability and environmental durability, especially when it comes to high humidity environments. With the best resistance stability under humid conditions and superior performance against temperature variations, they are ideal for critical applications where reliability is paramount, such as aerospace or medical devices. However, these advantages come at a higher cost, and tantalum nitride resistors generally have a more narrow resistance offering compared to other materials. Ruthenium oxide thick film resistors, while the most economical, offer the broadest resistance range. Their higher TCR and VCR values mean they are less precise than thin film's options, but they remain robust for general purpose applications, particularly where cost effectiveness and high power handling are priorities. Their performance in humid environments is better than nickel chromium, but inferior to tantalum nitride. Material selection for resistors depends on balancing cost, precision, and environmental demands. Tantalum nitride resistors lead in stability. Nickel chromium offers a versatile middle ground, and ruthenium oxide is ideal for budget-conscious designs requiring broad resistance ranges. Predicting resistance drift over time is critical for ensuring long-term reliability in electronic components. The SQRTSS methodology, short for square root of the sum of squares, provides a conservative approach for estimating worst-case resistance variation over periods of up to 1,000 hours. This methodology accounts for multiple sources of variation, combining them into a single prediction that avoids overestimation or underestimating drift. Typical worst-case values predicted by this model are 0.11%, 0.89%, and 1.87% after 1,000 hours under rated conditions. While useful in modeling, these predictions may not always align perfectly with the in-service conditions due to additional variations like operational environments or unaccounted for factors. The modeling approach combines time-dependent drift factors with equation 1, providing a robust framework for understanding and planning for resistance changes. This methodology is particularly valuable for engineers designing systems with the high precision or reliability requirements. The SQRTSS model is a powerful tool for predicting resistance drift, helping engineers make informed decisions about component reliability and ensuring designs can withstand long-term use under rated conditions. This graph represents a hypothetical model predicting resistance drift over time for a thin film resistor under controlled conditions. The example assumes a power rating of 1 watt, tolerance of 0.01%, and a TCR of 10 ppm per degree C. The model excludes long-term effects such as endurance drift to isolate the impact of standard power use. At 50 years, the model predicts a total drift of approximately plus or minus 0.4%, demonstrating the stability of thin film resistors even under extended operating times. Different power levels significantly influence resistance drift as seen in the graph. Resistors operating at low power levels, such as 0.1 watt, exhibit minimal drift, while higher power levels, like 1 watt, lead to more noticeable changes. This highlights the importance of derating operating components below their maximum rated power to reduce drift and enhance long-term performance. Thin film resistors provide exceptional stability, but the performance can vary based on operating power and certain specific operating conditions. Designers can minimize drift and ensure reliability by carefully managing power levels and accounting for predicted drift in long-term applications. Resistors play a critical role in electronic applications where stability, precision, and durability are essential. Based on the data and specifications reviewed, thin film resistors emerge as the preferred choice for applications demanding high stability, low tolerance, and minimal sensitivity to temperature and voltage changes. Their superior performance makes them ideal for precision circuits in industries such as aerospace, medical devices, and telecommunications. For environments where exposure to humidity or moisture is a concern, tantalum nitride thin film resistors stand out due to their robustness and resistance to environmental degradation. This unique capability ensures long-term reliability even in mission-critical applications requiring exceptional stability.